it's my pleasure to bring on stage Professor Dr. Sabina Jeschke. She's representing KI-Park, Quantagonia, and has the board member background at Deutsche Bahn. Please give her an applause. Sabina, great to have you.
Thanks.
And then we have Dr. Florian Neukart, the Chief Product Officer at Terra Quantum, with also a background in automotive industry at Volkswagen. Please give him an applause. No, you stay here, then I have the two of you.
Here.
No, inside. Perfect.
Okay.
Great. Thank you so much. And let's see, I hope we have also Norman in the line. I'm looking at our tech. Professor Dr. Norman Franchi. Norman, are you in the line?
Yes, I can hear you pretty well.
Perfect, there he is. Beautiful. Norman Franchi is heading the Department of Electrical Engineering, Electronics and Information Technology at the University Erlangen and the Institute for Electrical Smart City Systems and the Nuremberg Campus of Technology. Norman, I have to look in that direction, so you see us. We're very happy that you're on the panel and you could join. So let's start. We're talking about AI today and how quantum computing can be a driver. Maybe to make sure what we're actually talking about. AI is a buzzword. What do we mean when we talk AI? Maybe let's find a definition, a clarification for that. And I start with Florian, because you're smiling so nicely.
Yeah, so I mean, I hope you can hear me. Does it work?
Can you say something?
Yes, does it work? Yes, now it works.
Yes, thumbs up.
I mean, there are various definitions and pillars of artificial intelligence. But generally what we mean when we talk about artificial intelligence is we talk about systems that can learn, that can behave like a system with human intelligence, like humans. So we want to be able to have these systems, instead of being specifically programmed to do a task, learn from data to execute a task. We want to have adaptability. We want to make sure they can behave and adopt in changing environments. So be like humans, basically, and that's where we decide between artificial general intelligence and weak intelligence, artificial intelligence. So the artificial general intelligence would be a system that can execute many tasks. So it's not specifically programmed to learn only from one kind of data. It can generalize to multiple domains. It can learn from many kinds of data, be that images, be that other visual information, be that structured, unstructured data, whatever it is. Whereas a weak artificial intelligence that we all know about and use in business contexts is a narrow domain system. So it can only solve problems in a specific domain. Siri, for example, that we all have on our iPhones, could be classified as a weak artificial intelligence because it operates in a very narrow domain. Other language systems are also classified as weak AI systems. Image classification systems, predictive systems for predicting market behavior, all of these can be classified as weak AI systems, leveraging sometimes one pillar of artificial intelligence, such as machine learning, sometimes more pillars of artificial intelligence. So that's the general definition that I would give, and then of course, talking a little later about it, there is the quantum part that comes into it, but I think we'll get to that later.
Yes, yes.
Perhaps let me add one more point to that, because everybody believes that we are in the...
Excuse me, Sabina. Do you hear the audio? Because here we... Yes, perfect, thank you.
Oh, okay. So, I mean, there's so much talk on AI right now because we have this ChatGPT. And everybody believes that we have a breakthrough in AI right now, which, of course, to a certain degree is correct. But actually, the breakthrough in AI has been taking place about like 10 years before. Because this was the time when we came up with AI systems which were capable of dealing with what I would call for human-like complexity. So before we had this stuff in the lab environments or somewhere like in a shop floor, only a very limited amount of people allowed to come closer to the systems. But like 10 years ago, we saw the Google car. And we saw the Watson computers, and this was the time when we kind of saw that AI is really going to break through and is capable of dealing with our questions and the challenges we are having. So why do we have this situation right now? Because ChatGPT is kind of an iPhone moment. It's so easy to access, and everybody can do something with it, and it's cheap to a certain degree at least. So this is why everybody is using it. Everybody believes that now there's a breakthrough, but it has happened 10 years before.
Well, the question would be, you said it was an iPhone moment. Do you think with quantum computing, we had it briefly also before on that stage, do you think there will be an iPhone moment for quantum computing? Like the ChatGPT where everyone is surprised? What do you think?
So yeah, so with quantum computing we are now in an era where we can do or implement some of the use cases that seem to be promising. So we can solve problems in optimization that are fairly complex already using a combination of quantum computing and classical high-performance computing. If we do it the right way, if we solve these problems in a way where we leverage the right resources for the right parts of the problems, then today already we can see some benefits and potential. However, there is more to come. So there is much progress in machine learning that needs to happen still, so which hasn't happened yet. We start looking at deep learning algorithms where we take parts of it and run them on a quantum computer, but then still have a big classical part. That will always be the case. So for us, when we look at these problems, quantum computers won't replace classical computers, never. So everything that classical computers can do well today, they will also do well in the future. It's just about how you combine it the right way with quantum computers. And now this breakthrough moment, I think we have seen that already because the complexity of these problems that we're tackling nowadays, that's already remarkable. However, in the future, when we can tackle pharma use cases, when we can design individualized drugs, when we can bring it in and make, for example, free will possible in AI systems, which can be possible through quantum technology, then I think that will be the real breakthrough. When we can simulate materials for more efficient batteries, for example, or design megastructures, so things that we cannot build today. So I think these will be the ones where we really recognize what quantum computing on a large scale is capable of. So right now, doesn't mean we can't do anything, we do a lot of things, but there is a lot more to come. So I'm not sure if there is this one moment. It depends on the industry really that you look at.
So we're talking about AI, the progress of AI and how quantum computing can trigger that, a driver. But, I mean, we have two persons from quantum computing here, two experts. We also have Norman Franchi online. So I'd say there are more drivers to an AI than just quantum computing. And maybe Sabina, you want to do the intro to that. When we're looking at AI and the progress, what dimensions do we need to talk about?
Yeah. I mean, if you run a company and you want to come up with a overall full-blown AI strategy for this company, then it makes no sense to just look at AI of today, because today is yesterday by tomorrow. So the question is, how is AI developing towards what? Which kind of AI are we going to see in 2 or 4 or whatever years? We have to have a kind of an idea about that, and this is the basic for our AI overall strategy. So I always think about AI like a missile with 3 kind of firing engines. First is, and this is where we are right now, is algorithmically driven AI. Deep learning, Q-learning, R-learning, supervised learning, LLMs, and so on. This is all algorithmical stuff. And it will improve, of course, but this is where we are. And then what we are going to see, and I'm sure that Norman will step in here, is with 5G and 6G, okay, data rates get bigger, but latency time gets much, much smaller, and this is perhaps the most important point. So which kind of AI can I produce if I have a latency time which for the majority of applications I can just ignore? I mean, if you are supposed to program an autonomous car, where would you put the computer? Assuming that you have a 4G network, you put the computer in the car. Where would you put the computer if you had a 6G network? Perhaps in the car, but perhaps in some kind of cloud, because you can just ignore the latency time. So this leads to a totally new hardware approach, splitting body and brain with totally new security features. So this would be my second step, and then the third step is how to combine AI and quantum computing. We know that Moore's law is coming to its end over the next coming years, and then the question is, how are we going to come up with new hardware, and then we are in the field of quantum computing. So over to Norman with that.
Yeah, I would say, Norman, this is now up to you. We were talking about infrastructure, so maybe you can give us your point of view when it comes to the communications network. Where are we right now? What's the status? And what is needed to stay future-proof?
And maybe, hopefully, everyone can hear me quite well. So, yeah, I would shape it from that direction that is saying, who is generating the data that needs to be for example, analyzed, further processed than others. So, and where's then the computing done? And do I have to communicate in between? So means from an infrastructure point of view, so we have a strong need, and we already see this in our cities and somewhere else happening. We have quite a lot of data generated by new sensors, by cameras, by radar, by LiDAR, by multiple systems, not only these narrowband, what we call narrowband systems that have just a few amount of data to be delivered, but if you talk about having the city infrastructure ready that can have plenty of sensors in the night, in the day, and so on, for security reasons, for having an optimization in mobility, for navigation reasons, and so on. This is quite a lot of data. Plus, the end device, that is, for example, a sensor can be an end device, a car itself can be an end device. So this is what Sabine mentioned. In a well-infrastructured environment like Germany, maybe we will see in 5 years a quite good infrastructure available that can perform quite good assistance to autonomous driving. Maybe this is not everywhere available in the world, but in 15 to 20 years, we will see definitely a different environment and a different opportunity there. But in general, just to think about that I can process all the data that is delivered by a car as well, and to start learning on that, what was done, was that good? So in the framework of AI, so bring in some intelligence on that, what we need to find out if we not, as a human being, want to think about that, what is really happening. Because this is really an impact that we see from the science perspective. AI is helping us quite a lot with things that we cannot analyze analytically anymore, or we don't want to do this. So we have a big data problem coming with that our infrastructures are getting better and better and better, delivering more and more data over the upcoming years. And now we have to deal with these kind of data. Plus, we have to transmit them, or we have to communicate them. And if we want to react, a system like a car or a drone or whatever in real time, but the decision was made somewhere else in the infrastructure, then the latency counts. And this is exactly our sweet point, where we can then say, okay, if the decision needs to be done with the help of assistance of an AI algorithm, or plenty of them, the infrastructure should be ready for that. And today we have now the situation that the whole community, for example, the energy domain plus the communication infrastructure domain, they are currently in the situation to find out what are the best AI methods to have a certain solution for their problems. And we are just entering the market with that. But if you once have decided on that, where exactly the neural networks developed already 20 years ago, but we had no chance to process them in that short time, so having the hardware available, if we once know which algorithms are needed, then we are usually starting deploying our clusters, so our server clusters, where to process them. And if we are not ready for quantum computing at that point of time, I think personally we would decide for the wrong step. So we are bringing in a first step, just going with the data centers that we know, the supercomputers, and we have missed the chance to already incorporate the chances that we have with quantum computing.
So Norman, where are we? Sorry, at the beginning I couldn't understand. The audio was quite tricky. But when you say we need to make somehow like an integrated effort, what is your assessment of that now? Do we, like, where are we on a German level and maybe also on a European level? Like, are we still part of that race?
I think from a research point of view, this is definitely something where we have done a quite good job. But we have done this from a German and European perspective in so many other disciplines in the former years. Now the question is just about that. How fastly can we get some hands-on these technologies and in the stage where quantum computing is ready already today? And the interdisciplinary question is how to show the value in other domains which are really drivers. And this is what Sabina mentioned. 5G was a really big driver to do the communications. 6G is already on the horizon. And this is maybe an even bigger player, but how to incorporate quantum technologies and quantum computing in a 6G and 5G infrastructure domain, this is not solved yet. And here we have quite good researchers in Europe, but the question is, can we really then have some hands-on on the technology, and can we deliver also the technology, or have we the same problem like we had with 4G and with 5G, that how to apply the technology was driven by Germany and US, and the fundamental research was also done in Germany and Germany and Europe, but the technology was with America and with China. Mm-hmm. And here the question is, do we have a chance, and I think we have that, to also develop on the technology itself and have a technology footprint available in Germany and EU?
Thank you, Norman. Maybe I'll just bring that question to you. Do we have a chance? I hope the answer is optimistic.
Yeah, I think so. I mean, if you compare, when did we get the first research money for 5G compared to when did we start the rollout of 5G? And if you compare the same data for 6G, then we see that we started with the research on 6G much more early. So I think we learned something. We could move even faster, but we learned something. I'm a bit frustrated actually right now that we are not focusing much more on the satellite communication systems, because this will be the next big thing, 5G, 6G, and then the low orbit satellites. We see the Starlink. Imagine the situation in the Russia-Ukraine war without the Starlink. It would look totally different. We will see not Elon Musk, we already see him, but we see Jeff Bezos with 300 satellites going up in the next year. We see OneWeb, we see China, we see other places, and I cannot see European initiatives, or at least not very much. There is OneWeb from Great Britain, but so actually, yes and no. For 6G, we are doing a good job. For satellite communication, we are not.
Mm-hmm. Florian, anything to add on that?
So I will add to quantum technology. So in that sense, I think we learned a lot as well. So in the US, there is always this prominent VC funding that Europe seems to adopt now as well. So we see more VC funding coming, more startups being empowered, more or better transfer out of the universities into startups, into companies. So I see improvement there. Research, as everyone agrees, is great, but then what I always feel is a little behind is this transition out of research into the industry. But I think that's improving. I think it's going better, yeah.
But then let's talk about that, because when we're talking about AI, of course we're interested in the applications.
Yes.
So maybe just a brief definition. What's the difference between machine learning and quantum machine learning? Like, what will make the difference?
So I would make this distinction that so with classical machine learning, and as I say classical anything, I mean we don't use quantum computers to do anything. So we just use the classical high-performance computers, the cloud, the local systems that we have. And then when we talk about quantum, whatever, also quantum machine learning, then we'll add that to that stack. So it's not that we ignore completely what we have, but we just add that. We have an evolution of high-performance computing, if you will. And that's the difference. So we use for certain problems, for certain sub-problems that seem to be very complicated for classical computers, we use quantum computers. So in one aspect, you can achieve higher representational power using a quantum computer in a neural network. Not for the whole neural network, for parts of the neural network. So it means with a little effort, I can learn a lot more, I can learn more efficiently using less data, be more accurate, sometimes be faster. So these are the things that we look for. We can even generalize better, so find solutions that a purely classical system may not be able to find any time. So, and that's when we bring in quantum computing, not only for machine learning, but for all the areas that we look into in quantum computing.
And let's stick there, let's dive deeper. So when we're talking about applications across industry, where do you see the most potential? And please share use cases if you can with the audience.
So I always answer to that question in kind of four 4 steps. First step is we can run simulations which right now we would not even write because we would know that the runtime would be 20,000 years. And by that I would be dead and the computer would be broken. So like it's a digital twin of a part of the universe. We do not write these kind of simulations right now. With quantum and quantum algorithms and quantum machine learning, we can do that. This is my first point. So doing something we cannot do. The second point is real-time capability. If you imagine your R2 program, the schedule for the Deutsche Bahn, it can do that, and as a digital twin, not as a simple simulation. It can do that, and the computational time would be like 2 or 3 weeks, which means that you can use it for the schedule for next year, but you cannot use it to now, okay, in Stuttgart something is wrong, let's see, I have to swap this cargo with this regional. You cannot do that because you have 1 minute for the decision. So real-time capability for autonomous systems. And my third point is optimization. Whenever you run an optimization algorithm, let's say a traveling salesman or whatever, you give the computer a certain amount of time, computational power, and then within this time frame, you pick the best solution, which might be a very, very bad solution because the best one is here. But you pick the best solution you came up with and use it. And this, of course, is waste of human resources, of fuel, of whatever. So it's number 3. So finding the global optimum. And then number 4 is more general, enhancing innovation speed. I mean, usually if I ask you to come up with a new product for whatever, and I give you time to Christmas, then you know exactly if you want to run molecular simulations that you can only run a couple or perhaps several dozen of simulations. But with quantum computing, you can step through the whole solution space. And I expect that simulation and innovation processes are speeding up a lot, in particular towards also sustainability, sustainable materials and this kind of stuff. So this would be my 4 answers of application.
Mm-hmm. You want to add to that, Florian, maybe?
Yes.
And also if you can share some use case in quantum machine
absolutely.
learning.
I think I'll say in a few other words, so the same thing basically, it's simulation, optimization, machine learning. These are the areas that everyone is looking into in quantum computing. The most near-term ones are optimization and machine learning. Simulation is a little further out because it's the most complex problem that you can tackle, or one of the most complex problems that you can tackle in quantum computing. Looking at optimization, things that we do today, and I always talk about hybrid optimization algorithms, things that combine classical and quantum computing. So we look at logistics problems, we look at traffic optimization problems, parts distributions, we look at fleet optimization. So how can I manage a fleet and navigate them through a network of hubs? How can I minimize the empty routes of these vehicles, or empty miles basically, so that I minimize the number of vehicles in a fleet and maximize delivery capacity. That's an optimization. So then of course in simulation, so in physics you can also translate some of these problems, but we're not really there yet. So in machine learning we look at image classification, we look at automated detection of failures in production, for example. These are all state-of-the-art machine learning algorithms where they find application. And with quantum computing, we augment these. So sometimes we use simulated quantum chips, sometimes we use real quantum chips. Still, a big part is a classical high-performance computing aspect again. So the use cases are manifold, as I said. So anything machine learning that you can think about is a candidate for hybrid quantum machine learning. Anything where a system learns from data. One of the things that we did recently, for example, was a satellite navigation for a big company, European company. So here the goal was to optimize trajectories of satellites based on the missions that they had to carry out. So imagine you have satellites in orbit, and this one satellite or the satellite group gets the task of monitoring the weather. And there may be a mapping task, then the third one may come. So there's a wildfire that's emerging, you want to monitor that as well. How can I maximize the coverage for all of these 3 missions based on the number of satellites that I have in orbit? There's a nice optimization problem. It can also be formulated as a machine learning problem, and you can solve it with hybrid algorithms, and in that case outperform the purely classical ones. So it's really manifold, and these problems, all of them that I mentioned, you can still solve them using classical computers today, maybe not as efficiently, maybe not as accurately, but then in the future we'll see those that Sabina mentioned, or Professor Eske mentioned, when we think about material science problems, things that we cannot solve today. Battery chemistry, for example, drug design. How can I simulate quantum mechanically how a drug affects a protein in my body? I can't do that today. It's too hard for classical computers, no matter how powerful. With quantum computers, I will be able, and that will lead us to personalized medicine and many, many more interesting things. So I see much is still to happen, but we can do things today already. So, and I hope that helps a little in terms of the use cases.
Yeah, please.
Yes, please let me add one point, because this was the first example you once showed me, which you were running with Volkswagen, which I found so very impressive, and we were asking for very concrete examples. So what Florian did, it showed that the whole field of reinforcement algorithms can be improved by integrating quantum computing, which is a very interesting point. You know, everybody says something like, every newspaper starts with, oops, I can't do AI because I don't have data. This is totally wrong, because there are other AI methods, for example, reinforcement, where you don't start with data. You start with kind of simulations, you try around, and to try to find your, like a blind man's buff, you try to find your goal by trying around. So this is more or less how reinforcement works. Now, in a big parameter space, the problem with these kind of approaches is that it takes very, very long. So therefore, it's not used so very much. And when we started working together, he showed me that for Volkswagen production line, the paint job, you have all these robots. And if you want to train them, what they have to do, different models, you can either do the teaching, or you can use reinforcement training in order to reprogram them to different models. Usually this takes too long, but in combination with quantum computing, I learned my stuff from you.
Yeah.
I learned it from you. And with quantum computing, you can do it. And this is something, I like this example, because this is in the middle of German society and industry.
Perfect. No, thank you. This is exactly the tangible use case I was looking for. When we talk about timelines, so you said there are some things that we do today, some things in the future. Norman, you were talking about a timeline for the infrastructure. So everything has to play together if we say we want to have the next level AI. So let's try to find an answer to that. In terms of timeline, what are we looking at? Maybe, Norman, you want to start when it comes to 6G, like what do we expect? And then you guys can chip in.
Maybe to combine this also with a question about use cases, is that today every one of us knows that quantum computing could be a perfect solution and need to be a solution to get this encryption done. So with security reasons. Today, when someone, a car, my phone, or someone else is communicating, then usually the device is connected to a server somewhere placed in, globally, and then the data is processed, and we are asking for content. So means the high throughput is coming in the downlink. So the devices get something in the stream. So we get our network, Netflix streams, and others. So this is the we are driven since years in telecommunications that the data, the throughput is increasing dramatically, but mostly on the downlink. So we want to get information. This will dramatically change in the upcoming years already. So like I said, in the infrastructure, we have plenties of sensors. All the cars, all the consumers will permanently deliver in the uplink to the network data. So we have a heavily massive data problem that needs to be solved by AI, and then hopefully with that we can do this more or less in real time with the help of quantum computers. And from a 4G, 5G, 6G question is that our answer was to get this throughput handled to dense our networks. So even always smaller access points, better coverage, and so on and so on and so on. So we've blown up, or we are currently blowing up our terrestrial infrastructure, which can be easily destroyed, what we have learned in Ukraine, for example. And then we came up with non-terrestrial networks like satellites. And now I want to say that one thing is the computing is today done that the device is encrypting the data that needs to be delivered, is sent to a server, and then you do some processing. And in between, nothing is done, completely nothing. And this will change in the upcoming years. So the computing, like encryption, like, for example, data analysis on encrypted data and so on, will be done on the way of communications. And therefore, dramatically more computation is needed. And here I say that infrastructure will be blown up. Who's answering the energy question, an energy consumption question? I think here is a big room for quantum computing as well, because quantum computing is much lower in the energy consumption than traditional data centers and others. And on the other thing is maybe one last comment on that what can be in future is not only that we are communicating much amount of data and we have to drive with the energy consumption and so on, but let's assume that we do not want to communicate at all, because a quantum computer can deal with probability functions and probability distributions. So I can place one computer in US, one in China, and that doesn't need except a synchronization signal, nothing in between. But the probability can be quite high that both computers are calculating the same result. And this is a very interesting thing, because then I'm not limited anymore to the speed of light. And this is, for me personally, a super use case, maybe not discussed so far, but here I see really the beneficial things of quantum computing.
Better than the speed of light. Wow, Norman, I like that. Do you guys want to add to what Norman just said?
I mean, he was talking about the network technologies webs for quantum computers. You always say that we don't have to wait for them, they are already here. Yeah, of course, this is correct. A bit more general, I would say that we will see, there are two big groups of quantum computers. It's just deep temperature quantum computing, which you do not want to have in your living room because it's minus 273 degrees. And you will have them in clouds, and I think that we will see them coming up, as they are already there, but really coming up by 25, 26 something. And then we will see another group, and these are the low temperature or the room temperature quantum computers, which you can have in a car because they are insensible against temperature, but also against vibration. And we will see them 2028 about. Ask the guys from Section Q over there, because they are here and they build these kind of systems. So we will see these two groups. First group will be mainly hosted in clouds because of the necessity of cooling them. And then 2028 about, we will see the room temperature systems. And then we come back to the iPhone question, because at this point, I mean, the energy consumption of the systems will be very low. So there might be a question of, can't we have the Q phone or the iPhone as a Q phone? Can we do as much as possible on quantum computers, not because we need this amount of computational power, but simply because in terms of sustainability, it's much better to do as much you can on quantum computers. So this is perhaps my 2 cents for that.
Yes, so I would agree. So it really depends on the use case that you look at. So when we look at industrial use cases like optimization and machine learning, we can do that today. We have the systems in the cloud that we leverage. There will be advancements over the next 2-3 years where we then also see systems on the edge. So where we do edge computing, we will think about use cases where we have it on a mobile device. Right now, it's hard to conceive, so what would I use a quantum chip for on a mobile device, but there will be use cases. So currently when we train machine learning algorithms, we train them using these systems in the cloud, but then we deploy these trained systems, so we don't need a quantum computer to execute the trained model. However, there will be use cases where we have these chips on mobile devices, and that includes our phones. So where we see strong advantages, but there is a lot of developments that still need to happen. So for superconducting chips, we still have to solve room temperature superconductivity, which many claim they always solve, but for different times of technology, it may be earlier, but still, it really depends. So if it's industrial use cases, it's now, we don't have to wait for these systems that will allow us to simulate maybe drugs, allow us to do personalized medicine, will allow us to do material science really, give that 4 or 5 more years, and I think so, starting with 150, 160 error-corrected qubits, that may be interesting, but that's still a little way to go.
Maybe to summarize a little bit also what you said, so we're still talking about AI and how we can make an AI revolution happen in Europe without having the ChatGPT moment. So, whoa, it's there. It was super interesting, Norman, what you said with, let's talk about energy, like the energy that we will need for a future-proof communications network. We're talking about how to facilitate access to quantum computing. Maybe if we still talk about what are the challenges to have a responsible, meaningful AI revolution. Is there anything that you would add?
Mira, could you rephrase this question?
Yes, like what else do we need to make this AI revolution happen? We were talking about we have weak AI. What's needed to a general AI?
So I really think one thing that we have to keep in mind is what do we want to achieve with such systems? So, and then of course there come so many things come together. So how do you train these systems that they really do what you mean instead of they do what you tell them to do? So worst case scenario would be you have such a system and you tell them make everyone happy, and it manipulates all our brains somehow with some neurotoxin and we're all happy, of course, but that's not what we mean, certainly. No. So in that case, these systems will be much more powerful than current systems. So there's also a question, do I have to contain that system? Do I give it all freedom? Do I allow the access to all data that it can have access to? Those are all questions we have to consider. But then in terms of can we make it happen, I think that's sooner than later. Right now, when we look at, of course, what Sabina before mentioned, the large language models that we're using, they're still purely classical, and it's conceivable how they learn, how they execute. But then when you have a quantum computer that trains such systems, it's increasingly harder to understand how these systems learn, because we lose all that rich information of the quantum effects that happen during training once we finish this training. So it's not really possible to understand what happened, even for the people developing these systems. So hard to say when it's going to happen, but when it's going to happen, there are many positive things that will happen with such systems, but we've got to be careful as well and think about all the things that could theoretically go wrong and think about why would we even do that.
And this would be more the technological perspective. And then, of course, I mean, being capable of doing something does not mean that organizations are really going to do it. So starting to have kind of an overall AI, cloud, quantum strategy, check your organizations, whether you have the best people in your company or with whom, with kind of ecosystems you should do cooperation. So prepare yourself in kind of a 360-degree perspective for this quantum AI, whatever age. I think this is very important, because if you don't do that, you don't know where to go. And then come up with first use cases, filter them, and realize first use cases. If you don't have the capacity in your own house, hire whatever, who. But come up with clear use cases and also with first demonstrators. And from there, like in an iterative process, okay, now I have my first use cases, what was right, what was wrong, start the next ones. But at the end of the day, you need not kind of a lot of islands, but you need an overall strategy for this kind of topic. I think that this is a very important point. Being capable of doing something technologically is 1/3 perhaps of the problem, and then the work starts.
Wow, that was already almost like, I would say, the closing word. I would like to open the discussions and see if we have some questions in the audience. I learned a lot, by the way. Thank you so much for the deep dive. Yeah, and I'm just looking if we have some questions. Also to Norman. Thank you, Norman, for still being with us here. But I think you gave a lot to think about. So let's give them an applause, and thank you so much for being here.
Thank you very much for listening.
Thank you for listening.
All right. Thank you.